All right, welcome to the start of 211 material. So we're going to continue on now and talk about a couple of new topics. So we have about 4 topics you can see on the course website that we're going to go over. And the first one is center of gravity, and this is one of the things that we have been assuming we know its location, or we're given very idealized systems where we know, it's in the middle of a block, for example. But as you know, you're going to end up as engineers dealing with systems that are much more complicated. And one of the things that we need to know is where, for example, can we idealize the weight of the object, right? And so we usually do that by looking at the center of gravity. And so you might be familiar with different ways of conceptualizing what this is. But we're going to talk about it more from a mechanics point of view. So, if you imagine that we have a body composed of a bunch of particles, right? And so here, we've shown just one little piece of this big blob, and we idealize it as having some mass or weight, in this case, in the presence of a gravitational field that now has a weight dW. And the center of gravity is basically the sum of all of those, right? Which locates the resultant weight of the system as just one value. So this is a lot like equivalent systems where we idealize and reduce it down to a single value. And what this also means, right? So we can take our blob and actually discretize it into many, many, many pieces. Of course, probably actual cubes. And each of these cubes have some dW, right? So there's a dW here, dW here, and so on. And so that is what we'll put together here as the resultant, right? Now, what this also means is that the equivalent weight will also have to be balanced by an equivalent moment. And so if we look at this is a little bit easier to think about in 2D. So let's take a side view of this, slice through a blob. So let's say this is our blob, and look at it from the side, right? So I'm going to look at it this way, and hopefully you can imagine that has just some little bit of thickness associated with it. And so now we have all of these weights distributed, and we can think of those, right, as some distributed sets of forces, right? And so may or may not be uniform, but the whole idea, as you know, we can take this and turn it into an equivalent system, right? And so we can say that all those little teeny weights, we can sum them up and say that there's some equivalent weight here. And you know that in order for this to still be in equilibrium, it has to act at some point x, such that if you took all of the moments of the distributed load here on the left, they have to equal the moments for the equivalent system on the right. And so for the distributed load moment, we would take the integral of each of the individual little ones times their dW. So, each individual x, for example, right? And so on the right-hand side, the equivalent moment would just be x times W equivalent. And so if we put these two together and know that they have to be the same, what that means is that the integral of each of those little moments due to all the individual dWs that are acting in our system must be therefore equal, right, to the x W equivalent on the right hand side. And now we can actually solve for where is that x. So we did this exact same thing already when we looked at where would you put the equivalent force, right? So those kind of crane problems or the truck problem that we did a while ago. And this actually is the definition of the center of mass, right? Formally speaking, this is where it comes from. And so we can look at all of the definitions, and of course in 3D we would expect to have x, y, and z. And you might be familiar with different versions of this where we can look at center of mass, center of volume, and also center of area depending upon our system. So let's talk a little bit about how we go from center of mass to center of area and what the relationship is between those. So we know that force, right, for us, this is force due to the weight, right? And we know that weight is mass times gravity, right? And mass, just by our definition of density, is density times volume, and then now we multiply it by g. So this is equal to mg. And now if we take some of our definitions that we started to establish, we see that the centroid in the x direction, for example, or the center of mass, is going to be equal to the integral of x with respect to all the individual ones, df, over integral df. Recognizing again here that f equals w. So this is what we just derived up above, right? And so this is integral x dw over integral dw. And now if we go ahead and substitute what we have here, we see that we have the integral of x bar, right? And now for dw, I'm going to take the derivative right here, right, of the rho vg. So it's the derivative of rho vg over the integral, the derivative of rho vg. And this again is equal to x bar. So what assumptions do we make, right? So if we assume gravity is constant, which if we will, if we're here on Earth and at roughly the same elevation, then we know, so if g is constant, we're going to make a couple of assumptions. The first one is assume g is constant. So what does that mean in terms of the integral? It means it's going to come out, right? So if we take out the g from this equation here, right here, and right here, it's on the top and the bottom. So essentially this equation now simplifies to x bar is equal to the integral of our little x, d, now rho v, over the integral d rho v. And that's where now we're getting towards something that looks a little bit more like the center of volume equations that we see up above. So what that means, if we just take rho v, what this actually means, right? So just by our equation of density is equal to mass over volume, if I substitute in, then what I'm actually going to get is that this is equal to dm, right? Or the integral dm. So therefore, the center of gravity, and remember these are locations, right? They're not values, it's not what is the equivalent weight, it's where is the equivalent weight. The center of gravity is actually equal to the same place as wherever the center of mass is. All right. Now, let's also assume for our objects that density is constant. So if density is constant, what that means is that we have what's called a homogeneous material. It's made of the exact same thing everywhere. And if this is true, right, if density is constant, then we could go back up to this equation here, right? If we still assume gravity is constant and density is constant, then all that's going to be left is the volume. And so what that means is that the center of gravity is equal to the integral of x dv over the integral dv. So therefore, center of gravity is equal, its location is essentially wherever the center of volume is. It just means it's a function of the geometry. It has nothing to do with mass anymore, right? Because the mass is constant everywhere. So the location of the center of gravity, that balance point, the tipping point, as you might think about in these cases, if this thing was made of all one material, it really just has to do with the shape of the object. And then, of course, we can say that volume, if we say volume is equal to area times some height. So this would be the case for objects that are symmetric, for example, right? Like a cylinder or something that's sort of extruded where it has some constant cross-sectional area and then it's just that long, then then we can think about the volume this way. And so now if z is constant, then we only have to really think about the cross-sectional area. And so then x bar becomes integral of all the little individual ones, dA, over integral dA. And so what that means is that the location of the center of gravity is equal to the center of area. And so this is what brings us now to the concept of the centroid. So the centroid is that point defining the geometric center of an object. And we're going to make all of the assumptions above when we look at our objects. And so what that means is the centroid is essentially the center of gravity point. And again, only if the material is homogeneous. And if it has an axis of symmetry, then we know that the centroid is actually going to lie on that axis. So the obvious example here is a rectangle that you see in the top right of your screen. And we all know that the geometric center, right, is right in the middle here, and that's also corresponding to these axes of symmetries. We know that's not the case, for example, for a non-equilateral triangle. Here in the case of the cylinder, the axis of symmetry is right in the middle. And so here, and then in this case, because it's b over 2 and b over 2, we know that the center of gravity is going to be right in the center of this cylinder. Now, one thing to remember or note, it's not exactly intuitive, is the fact that for a lot of 2D type objects, so like lines or wires or cables or rods, especially rods that are bent, it turns out that centroid is not necessarily located actually on the object itself, right? So the balance point is actually at some other location outside of the object, and so that is also a possibility, right? And so what we're going to do now is just go through the actual derivation of how you would find the centroid for a variety of shapes, and then we'll do some applications in the next couple of lectures. So this is just